Okay, so today we're going to continue talking polynomials. We're doing other than this is big time SVAC stuff. So here's our SVAC review for today. It's just focusing on polynomials. Okay, what have we done in the past? Let's put this in perspective. We've defined polynomials. We know how to classify them by degree, base power of x. We know how to click all of those Chromebooks all the way close, please. We can pick out leading terms, leading coefficients, constants, etc. We can write them in standard form. We know what the definition of a polynomial is, right? All of the coefficients have to be real numbers, and the powers have to be whole numbers, right? But we don't know how to solve polynomial. Well, we do. We know how to solve some polynomial equations. Without even knowing it, you've already done a lot of this. This is a polynomial equation, right? That you didn't know it was at the time, but you've solved stuff like this. What would I do to solve that equation?
Push everything over.
Okay, push everything over to the left side, right?
Yeah.
Okay, so I would subtract 2x from both sides and subtract 14. So I'll put it into standard form, right? Okay, so it's in standard form, and now it's a polynomial. It's quadratic, right? We would have called that a quadratic trinomial, a month ago. But now we would call that a polynomial, right? It is a trinomial, but it's a quadratic polynomial. Quadratic just means that it's second degree, that the biggest power of x is x squared. Okay, we already know how to do this stuff. So let's talk about how we would solve that one. What would our strategy be? Now let's go back. Okay, small note here. I'm going to award a little more partial credit on one of the Chapter 5 tests. On the one where you're choosing the best method for solving a quadratic. If you put down, for one like this, if you put down the quadratic formula, that should not be worth no points. It's not the best method. There is an easier way, but I'll make it worth like half credit or 2/3 credit or something. And I'll automatically regrade all those, so your test grades might go up a little bit from that. So we can always use quadratic formula. Anytime we have a quadratic equation in standard form, quadratic formula always works, but what's easier here?
Completing the square.
Well, completing the square, I tell you what, I'm going to make that optional too.
Zero product. It's going to work.
The zero product problem, we can factor. If you like, and I know some people like, which I think is good, like completing the square when it's easy to do. I do. It's a good idea if that's one and that's even, right? Then it works pretty well. But even then, if you would rather just use the quadratic formula, I'm okay with that. Just get good at it and use the quadratic formula. That's okay. But in this case, we could find magic numbers and factor. What would they have to multiply to?
14.
No.
5.
Not 14.
Negative 14.
Negative 14. They have to multiply to negative 14 and add to negative 5. What are those? Negative 7, positive 2, right? Okay, so that one does factor, and that's much easier than having to go through the whole process of quadratic formula and simplifying the radical and the whole bit, right?
What do you do after that?
Say it again?
What do you do after that?
Okay, so after this, then all we have to do now is just set those equal to 0 and solve. We're going to apply the zero product property, right? Look what we did here. Caleb, what we did here is we wrote this as a product of factors that equals 0. What's the only way two things can be multiplied and get 0?
0.
You got to multiply by 0, right? So either the first factor has to be 0. What value of x makes the first one 0? 7. So if x is 7, we get 7 minus 7, so we get 0 times, who cares? 0 times something else is 0. That's one solution, right? Or the other possibility would be that we multiply something times 0. Well, what would make the second factor 0? Good. So we get two real solutions, okay? Now, what do you expect? So if we write a polynomial equation in standard form like this, Willie, if this is going to be, so really this is my polynomial function that I'm setting equal to 0, right? So we could, if we wanted to, we could call this thing right here f of x or y or something, right? By setting this equal to 0, we're asking the question, when does f of x or y equal 0? Where does that happen in the xy plane? Where is x equal, or y equal to 0, sorry? Okay, on the x-axis, right? Every place on the x-axis, the y value is 0, right? So what's going to be unique about these two numbers then? What's happening at x equals 7 and x equals -2? What's going on? Y equals 0. What do we call those places where y equals 0 on a function? They're cutting through the x-axis. What do we call those? X. What do we call them? X-intercepts, yeah, right? All those x-intercepts. So there they are, right? If I were to graph this parabola, A is positive, so it opens up, and really, this is all we need to know in this case is that it cuts through the x-axis at the x-intercepts, -2 and +7, right? So real solutions of our polynomial equation correspond to x-intercepts, right? Real zeros, places where the function is equal to 0, correspond to x-intercepts, right? Okay? Let's look at another one. How about that? Some more practice. We've done a lot of them like this. Carlos, what's our strategy going to be to solve this quadratic equation? You got this. This is no big deal. You got this. This is a little different. This is an easy kind, right? What do we do here? You can even just tell me the steps. What would you do to solve for x? So, yeah, what are you saying? You're on the right track. +4, exactly. I'm going to add 4 to the other side. Good. Okay, then what? Square root, right? Okay, I'm going to square root. So the whole point there is I'm isolating x, aren't I? Because I can point to a single x, I'm just isolating x. What are the two steps to get the x by itself? I'm going to add 4 to chase it to the other side, and then I'll square root, right? And so what do I get if I square root both sides then? X equals, say it again? Plus or minus 2. Square root of 4 is 2, right? Okay, so I get real solutions at 2 and -2. So, Kaylin, what do you think must be going on the graph then at +2 and -2? That's where the function equals 0, right? So what's that mean then? What's going on there? If I graph x squared minus 4, what's happening at +2 and -2? Say it again? Intercepts, yeah, x-intercepts, good. Okay, so we got, there's our x-intercepts at -2 and +2, right? Okay, good. We're seeing a pattern. How about this guy over here? What are we going to do there? Same kind of stuff, right? Here, what do I do to solve for x here? This on the right, not that one. It's all real similar. Subtract 4. Then what? Square root it. Okay, so if I square root both sides, so that's going to give me x equals, I got to do plus or minus. Yeah, what's that doing? I'm getting i's, good. So I'm getting i's out of this, and the square root of 4 is 2, right? Okay, now this is a little different. I want you to see the difference here, right? Now we got two answers, plus 2i and minus 2i. Are those numbers that show up on the x-axis? No, the x-axis only has real numbers on it. So this one had 2 zeros, but the zeros were imaginary. Do you think it has any x-intercepts? No. It doesn't. You're right. Notice this one, it never passes through the x-axis. So we can draw an important conclusion here. We've mentioned this before, but maybe it's more clear now. When we get real zeros to a polynomial equation, they always correspond to x-intercepts. When we get imaginary zeros, they don't. They still work though. What does it mean to be a solution to this equation or a zero? It means if I plug these back into the original equation, they're going to make that function equal 0. Let's show that it works. If I take, for example, positive 2i, that's one of my two answers, right? So if I plug 2i in for x, what's going to happen? Let's get it out of the way a little bit. So if I plug 2i in for x, I'm going to get, instead of x, I'm going to get 2i squared plus 4. and we want to show that that equals 0, right? Well, how do I square 2i? What do I have to do?
Distribute.
I've got to distribute the power, right? So I'm going to distribute the exponent to the 2 and the I. So that's going to give me 2 squared is 4 times I squared
Just -1.
plus 4 equals 0. But what's I squared equal to?
-1.
-1, right? So 4 times -1 is -4 plus 4. That does equal 0, right? So it worked, right? So the zeros, they still work. They're just not x-intercepts. Both of these answers, if I plug them in, still make the equation true. They just don't show up on the graph as an x-intercept. Okay? All right, how about one like that? What am I going to do there?
Just everything.
What am I going to do?
Factor 0.
Well, maybe. But what do I have to do? Before I do anything else, what do I have to do?
Push everything to the left.
I've got to add 4. I've got to put it in standard form, set it equal to 0, right? So that's always going to be our first step. So if I add 4 to both sides, I get x squared minus 2x plus 5 equals 0, right? Okay, so we'll look for magic numbers. Are there numbers that multiply to 5 and add to -2? No. No. So what are our options then? We can't isolate x. We can't factor with magic numbers. So what are my two options? Complete the square, or
Quadratic.
you take your pick. I don't care. What would you prefer?
Quadratic.
Quadratic formula. Okay, let's do quadratic formula. That's fine. So if we're going to do quadratic formula, we get ax squared plus bx plus c equals 0, right? It's in standard form. So now remind me, what's the formula? Warm up your pipes here. X equals
Plus or minus square root b squared minus 4ac divided by 2a.
Good. Okay, all divided by 2a. Good. So we'll just plug in our values, right? So what do we get? A is 1, B is -2, C is, okay, plug them in, see what we get. So negative B would be 2, plus or minus the square root of B squared, 4, minus 4 times 1 times 5 would be 20.
20.
All divided by 2 times 1 is 2, right? Okay, so that's going to give us 2 plus or minus the square root of -16 all over 2, right? So let's split this apart. Phones ought to be away, please. I got eyes in the back of my head.
4i.
Plus or minus, what's the square root of -16? 4i. Right? Okay? So 2 over 2 reduces to 1. 4 over 2 reduces to 2. And those are my two answers. Okay, am I going to get x-intercepts for that one? No, I'm not. I get i's in my answer, so I won't, right? I get two solutions, but they're complex. All right, with imaginary parts. Okay, so this is no sweat, right? You guys have got this stuff. So far, so good. You can do all these. Okay, this one's a little bit different. This one is no longer quadratic. What's the degree of that polynomial equation? Cubed, or 3, right? Okay, so we get a cubic polynomial or a third degree polynomial. So this looks pretty similar, though. We've done some like this. What do you think I do with this one? What's a possible strategy for solving for x here? What do you think? I mean, you've done a bunch like this. What do you think, Kate? Okay, well, yeah, I mean, you're right. Maybe we'll have to factor. Is there something else that we might initially try? I mean, we did some other ones like this. Like we did, like what about that one? What did we do? We isolated x, right? So do you think it's possible we can isolate x there? Okay, what would the steps be? So first I would add a, okay.
Cube it. Cube root it.
Okay, now cube root, good. So now I'm not square rooting, I'm cube rooting. We haven't talked about cube rooting stuff yet. You can do it though. But there is one, we'll talk about this more in the future, but I'll tell you this little tidbit right now. When you take an odd root of both sides of an equation, so that means like a cube root or a fifth root or a ninth root or an 11th root, as opposed to an even root, like a square root or a fourth root. Whenever we take an even root, like we've done with square roots, we have to include a plus or minus. You don't with an odd root. Okay, so if I take the cube root of both sides, I would only get one answer, and it would be x equals what?
2.
2, right? 2 is the cube root of 8, isn't it? 2 cubed is 8. So I get one answer. Well, that's easy. So that must be an x-intercept, right? If we look at a graph of that function, sure enough, there it is, x-intercept at 2. Okay, but you don't know this yet, but we're missing some important information there. Okay, and here's where it comes from. The fundamental theorem of algebra. Okay, what this says, let's summarize. We'll read through it once and then I'll summarize it, just to pick out the important parts. So it tells us every polynomial function of a degree n greater than or equal to 1 has at least one zero where a zero may be a complex number. So it might have i's. Okay? More importantly, the second part, the corollary, every polynomial function with a degree greater than or equal to 1, not only does it have to have at least one zero, it has exactly n complex zeros, including multiplicities, and we'll get to that a little bit later. Okay? So, look back at the examples we've done so far. Let's just briefly review these. This was a second degree polynomial, right? How many zeros did we get? 2. Okay, not an accident. Both of those were second degree polynomials. How many zeros did we get? 2 and 2, right? Okay, that was a second degree polynomial, and once again we got 2, one for the plus and one for the minus, right? We got 2 complex zeros. What's the degree of that polynomial? What's the degree of this one?
Oh, no zeros?
Well, what's the degree of the polynomial?
3.
3, because the biggest power of x is 3, right? So if the degree of the polynomial is 3, how many complex zeros do we have to have? 3. We only got 1, right? So isolating x didn't work great in this case. It was okay. If we were only looking for x-intercepts, for real zeros, it's fine. We got it. But if we're looking for all complex zeros, which we are going to be looking for, that's not good enough. It didn't work, right? We got to find the other 2. They're missing from our answer, right? How do we do that? Okay, here's how we do it. We have to factor. And it's strange that we do because we haven't had to in the past with something like this, but we do now. So I'm gonna drop some factoring patterns on you here. I want you to watch this very closely and you'll get these. They're not hard. 2 of them you already know. 2 of the 4 you already know. First one you already know because it doesn't exist. If you have a sum of squares, a pattern that's a sum of squares, like let's say x squared plus 5 squared, x squared plus 25, what's the factoring pattern? Well, there isn't one. Anything that would fit the pattern of a sum of squares never will factor. Okay, done. What about a difference of squares? This is a difference of squares because a difference means you're subtracting, right? It's something squared minus something squared means a difference of squares. Okay, this one you already know in reverse. We already talked about this one, fairly recently when we talked about multiplying polynomials, right? We did it backwards. We said that if you multiply 2 factors that are conjugates, a plus b times a minus b, then you always get back a difference of squares for your answer. So we can reverse the direction of that and factor. That also means that anytime you see 2 terms that can be written as something squared minus something squared, it's always going to factor using that pattern. Let's go back and look, for example, at this earlier one that we did by isolating x. So let's take this guy, x squared minus 4, right? If we take x squared minus 4 and we apply that factoring pattern, we should get the same answers. We should get plus 2 and minus 2. So let's show that we do. Okay, so real quick, what's the pattern again? Remind me what the pattern is. Difference of squares. A squared minus b squared factors how?
A squared.
A plus b times A minus B. Okay, so if we're going to take something like x squared minus 4, and we're setting this equal to 0, right? We want to solve this by factoring it using the zero product property. Okay, first of all, we have to ask the question, can we write this as that pattern? Could I write it as something squared, call it A, minus something else squared, call it B? Well, what squared gives me back x squared? X, yeah. So x is like A, right? Well, what do I have to square to get 4? 2. So 2 is like B, right? And so if we factor this thing, we're just going to get this pattern. So A plus B becomes what? X plus 2, right? X plus 2. A minus B becomes X minus 2. And if all that stuff is equal to 0, well then by the zero product property, what are my solutions? X equals negative 2, X equals 2. So it works, right? Just like this way worked, the other way works also. Why would you do it this way? I mean, I wouldn't. I would just isolate X. In the future, there will be a couple cases where we'll need this pattern, but not often. Really not often. Okay, that one's not a big deal. Okay, the other two, though, are more important. Right? Turns out we needed these because we ran into a situation where when we didn't use them, we didn't get all our solutions, right? Okay, yeah, you're gonna go. Okay. See ya. Okay, so watch this closely. Here's how these patterns work. So whenever we have one of these cube patterns, so either a cubed plus b cubed or a cubed minus b cubed. I haven't even put in the operations yet, because I don't want you to get confused by those yet. Look at the way the pattern always works. It's always going to factor, if I have a sum or a difference of cubes, the first factor is going to be a little one. It's only going to have 2 terms. The first term is an A and the second term is a B. That's easy, right? The second term is quadratic. It's a little bigger. It's got 3 terms. First term is A squared, last term is B squared, and the middle term is just A times B. Not 2AB, just AB, okay? Here's how the signs work with that. If it's a sum of cubes, so we're going to factor A cubed plus B cubed, whatever the sign is between the cubes, that's what always goes with the first small factor. So it would be A plus B if it's A cubed plus B cubed. The next one is going to be the opposite, so it's going to alternate. And the last one is always positive. Okay? So what do you think the difference of cubes pattern is going to look like then? What do you think?
A minus B, A squared plus AB plus B squared.
Exactly, right? So once again, whatever shows up there is matched there, and this one's the opposite, and the last one's always positive. Okay? So now we can use these patterns. Let's see, so we're doing A cubed minus B cubed, so let's use this guy right there. Okay? Okay, so now here's how we got it. I know this is a lot of stuff today, but just stay with me on this. Okay, so if we want to try to factor something like this, now notice that all of the factoring patterns are sums or differences of 2 terms, right? And there's only 3 of them. Remember, that's not a pattern. This one's a no-brainer. These are the 2 that you got to really focus on, right? They only have 2 terms, though. So when I'm trying to solve a cubic equation like this, where I've got 2 terms, it only is going to possibly work for 2 terms, and I just have to see if it does. What's the only pattern that could potentially fit this one? I mean, without even looking at the last part, I have x cubed minus something. So what's the only pattern that could have a chance of working? Of the 4 patterns we just looked at. Could it be a sum of squares? It couldn't be a sum of squares, right? Because that's not x squared, it's x cubed. The only thing it could be is a difference of cubes, right? It's x cubed minus something. So the question is, does it match that pattern? Could we write x cubed minus 8 could we write that as a cubed minus b cubed? What would my a be? Okay, what's my b? 2. Yeah, 2 cubed is 8, isn't it? Right? See what I'm saying? Okay, so can we write 8, because it's 2 cubed, this one works. Now if I gave you a different one, what if I gave you something like x cubed plus 11? That's not going to work, because 11 is nothing cubed, at least no convenient integer cubed, right? See what I'm saying? Okay, so that one we wouldn't be able to apply the pattern to, but this one we can. So what's the pattern tell me? Okay, so I'm going to get back a minus b, so what's that going to look like? X minus 2, right, because b is 2, times a squared. Well, what's a squared going to be? X squared, good, plus a times b. X times 2 is what? 2x, plus b squared. 2 squared is 4. Okay? Right? Got the idea? Okay, so now I've got this thing factored. I can just use the zero product property. Let's see here. So what are we going to get? Brett, what's going to be the zero? What's the zero of the first factor? If I set that equal to 0. 2. There we go. Okay, that one we knew already, didn't we? Right? That one we already knew because from earlier we decided that we knew that 2 was the x-intercept. That was the one real solution that we got, right? So that one's taken care of. But we've got this other factor over here. Now something I got to tell you about these patterns that's important. In the difference of cubes and the sum of cubes patterns, the big factors in those factoring patterns, the quadratic ones, those are always going to be irreducible quadratic factors. Big words. What's that mean? They're never going to factor any further, and they're never going to give you real zeros. They're always going to give you imaginary zeros, and you don't even bother trying to factor them. They never will. So for example, this guy right here, are there magic numbers that multiply to 4 and 2? No, there aren't. I don't even have to bother trying to find them because they won't be there. Okay, Patrick, what do you think I could do with this then? So if I'm setting these factors equal to 0, this one is not going to factor. If I set that factor equal to 0, how am I going to solve it? I can't because I have an x squared and an x. I mean, I could complete the square. That's one I could. That's fine. I could complete the square because that's a 2. I'm either going to have to complete the square or what's the other alternative? Quadratic formula. There you go. Right? So we haven't completed the square yet. Let's do that. So if I complete the square, I'm going to push the 4 over to the other side, right? And let's see, I know that I have to make the left side turn into a perfect square trinomial. Well, what's going to be the value of x that goes, the number that goes with x? It's going to be 1, isn't it, right? To make that happen, though, I've got to create a perfect square trinomial up here, so what number do I have to include? 1, because 1 squared is 1, isn't it? Right? Whatever that number squared is. And now let's just make sure it works. What two numbers multiply to 1 and add to 2?
2.
Multiply to 1 and add to 2. 1 and 1, right? So 1 and 1. There's where I get the square, right? On the other side, I've also got to add 1 because it's an equation. So on the other side, I get, what, -3? Okay, and so then I'm just solving, setting this equal to 0 and solving. What am I going to get? Square root both sides, right? So what am I going to get? So square root of 3, but what does that become? I, okay. So I'm going to get on this side, I'm going to get square root of 3 plus or minus, right? Plus or minus 3, square root of 3 times I. On this side I get X plus 1, last step? Subtract 1. So I get x equals negative 1 plus or minus the square root of 3 times I. How many solutions are contained there? 2. 1 for the plus and 1 for the minus, right? So that's all 3, isn't it? Right? I've got x equals 2, or now I've got x equals negative 1 plus the square root of 3i, or x equals negative 1 minus the square root of 3i. I got them all, right? Everybody see that? Okay? Let's try one more. How much time we got? Yeah, we got 2 more. How about that? Really, what's my strategy going to be here if I'm trying to factor this?
There's no 0 at the end?
Okay, so I could put a 0 there. That's fine. If it's an equation, that's fine. On some of these questions, though, just so you know, on Moodle, some of the time I'm just going to tell you to practice factoring. So I'm going to say write that in factored form. Okay, so let's not put a 0 there for now. It's only really useful. It's a good point you make, because really this would only make sense to do if we're solving an equation, right, where it's set equal to 0. Okay, but what does this possibly factor into is my question. Yeah, I'm going to put the 0 back. Okay. So how are we going to do this one? I can't isolate x, can I? Because it's cubed. Okay. Right. So what am I going to do? I remember saying that. It might come into play at some point. John, what do you think?
I would say isolate x, but
We can't do that, you're right. Yeah. Okay, Landry, what do you think? I'm going to do the sum of cubes, aren't I? Right? So I have to factor this, and the only pattern that could work, I've got x cubed plus a number. So the only pattern that we could use would be a sum of cubes, right? Okay, so let's try that and see if it works. So can I write this as a cubed plus b cubed?
Yes.
I can. What's my a? X. What's my b? Yeah, okay, I just happen to have a list of perfect cubes over here. So just, what are the odds of that? So like 5 cubed is 125, ooh, yikes. 5 cubed is 125, 7 cubed is 343, 9 cubed is 729. They grow fast, don't they? Right?
Yeah.
Start cubing numbers, they start to get big in a hurry. So I can write this as a sum of cubes. So what's my a and what's my b? Once again, a is x, b is... Oh, I wrote 7. I was supposed to write 9, wasn't I? So then what's my pattern going to be? I've got a sum of cubes. So what goes in here? What goes in here? Let's see. I'm going to pick on somebody here. Lauren, what's going to go in here? I've got a cubed plus b cubed. So what goes there? X plus 9. Very good. How about here? Is x squared. Good. Minus. Good. 9x ab plus... What is that? 81. There you go. Okay, perfect. Right? And if I want to find the zeros then, here's the real 0. What value of x makes that? Negative 9. So this is going to have an x-intercept at negative 9, right? And then this guy here, we would probably have to use like the quadratic formula, right? So let's do that. So for this one, we'd get x equals negative b plus or minus the square root of b squared. What's negative 9 squared? 81 minus 4 times 1 times 81 all over 2 times 1 is 2, right? If I'm setting this equal to 0 and solving, right? Everybody see what I'm doing? Okay, so we can simplify this. 9 plus or minus the square root of 81 minus 324 is going to be 200 and, what's that going to be? 243. Negative 243.
Yeah.
Okay? Right? So I can split this apart into separate fractions. 9/2 plus or minus. The negative is going to become an I, but let's simplify the radical. 243. Let's make a factor tree. What's one number for sure that goes into 243?
1.
Well, other than 1. What is it? 3 does, yeah, because 2 plus 4 plus 3 is 9, which is divisible by 3. Right? So 3 times 81, actually.
81.
Right? And what does 81 break up into?
9. 9 radical 3.
So we get couples, a couple and a single, right?
9 radical.
Couples go out, so we get 9 radical 3. Good. So we get 9/2 plus or minus 9 radical 3 over 2 times I,
Sure.
right? Those are my two other answers. Okay. Now, did you notice something here? One last pattern I want you to see. Whenever we ended up getting imaginary solutions, let's look at every instance where we did. Look at this. 9/2 plus or minus 9 radical 3 over 2I. Those are conjugates, aren't they? I get the first term plus the second term, first term minus the second term. Let's take a little stroll down memory lane here. If I go back to this one, notice what I got. Conjugates, complex conjugates. Complex conjugates because they have I's in them. But you know what I mean when I say conjugate. It's the form A plus, well, it's always going to be this form, A plus BI. So -1 plus radical 3I. So A is -1 and B is radical 3, right? And A minus BI. Every time I get that, when I get complex solutions, they always come in pairs. Look at all of these. How about that one? Same thing. A plus or minus B times I, right? How about even that one? I got the answers plus or minus 2I, but isn't that the same thing as 0 plus or minus 2I, right? A plus or minus BI, every time. Same thing, those were real, right? See what I'm saying? So when this tells us something pretty important. So in this fundamental theorem thing we're talking about, if I have a 5th degree polynomial, how many complex zeros does it have? No, exactly 5. Guaranteed it has 5, right? So if the imaginary ones have to come in pairs, Carlos, close that up. If the imaginary ones have to come in pairs, what are the possible number of imaginary zeros I could have for a 5th degree polynomial? I'll start you off. I could have none. I could have no imaginary zeros. And then I'd have how many real ones?
2.
Well, no, if I have a 5 total.
Well, from what I think, it's 20.
5, right? Because they have to add up to 5. The total number of zeros has to be 5. So if there's no imaginaries, then there's 5 reals, right? Now the next number, I couldn't have one imaginary. They have to come in pairs. So I could have 2. If I had 2 imaginaries, how many are left over to be real then? 3. So I could have 2 imaginary, 3 real, or I could have 4 imaginary and 1 real. So if it's a 5th degree polynomial, I'm always going to have at least 1 real 0, which means I always get at least 1 x-intercept, right? It's going to be that way for every odd one, isn't it? Right? Because if it's odd and I can only have an even number of imaginary ones, there's always going to be at least 1 leftover real one, isn't there? Right? Okay, good. Whew, that's a lot of math. That's a lot of math. That's kind of cool stuff, though, don't you think? You got to embrace your inner geek sometimes and just allow yourself to be impressed by math.